Hello friends, welcome to Zeta Axis, and today we will discuss about Earth's internal structure. In this topic we will see the planetary differentiation process, the structure of crust, structure of mantle, structure of core, then we will see the concept of convection cells, and then we will see the distribution of our elements and minerals within our Earth. Now let's begin with planetary differentiation process. What happened when the Earth was formed? It was a hot ball of molten rocks, mainly because of the heat generated during formation of our Earth, as well as collision of a large number of meteorites. Now, because of this, the temperature of our Earth increased above 1500 degrees Celsius. This is a very high temperature. At this temperature, even the hardest elements, even iron, is in a fluid form. Now, because they are in fluid form, they could easily mix with each other, they could easily move from one place to another. So because of this, what happened that the heavier elements which were on the outer surface, they came to the inner parts of our Earth, while the lighter elements, they moved on the outer regions of our Earth. So we see the elements got distributed based on their densities. So when later Earth cooled, we saw that a layered structure was formed. In each of these layers, there are rocks which have similar properties, have similar densities, and when you will see that the density of our Earth increases as we go from surface to the core. Our Earth was formed around 5 billion years ago, and when it was formed, it was a uniform ball of hot rock. There were several factors which increased the temperature of our Earth by above 1500 degrees Celsius. Two of the most important factors we have already discussed. Radioactive decay was another factor. There were a lot of radioactive elements within our Earth, and these radioactive elements undergo decay process. When they decay, they generate a lot of heat. This heat was added to the heat from other sources. Then there was tidal forces of sun and moon. What happens when our Earth revolves around the sun? It revolves in an elliptical path. The distance of our Earth from sun varies. The distance is minimum over here, maximum over here, and therefore the gravitational force applied by the sun also varies. The gravitational force is maximum over here because it is closest point, while it is minimum here because it is furthest away from the sun. Because of these changes in the gravitational force, we can see that there is slight change in the structure of our Earth. And because of this slight change, what happens that the internal layers of our Earth are moved against each other, generating a lot of friction, and this friction generates heat. We have already seen that a lot of heat was generated during formation of our Earth. There were a lot of small planetoids which came together to form our Earth, and this led to a lot of collisions and generation of heat. Moreover, when our Earth was formed, at that time there were a lot of meteoroid collisions also, which generated the temperature of our Earth. Now, because of this high temperature, there was planetary differentiation. Because of this, all the elements were in fluid state. They were able to move from one location to other location very easily. The less dense elements were able to rise up and come to the surface, while the more heavier elements were able to sink in the deeper parts of our Earth. This is the internal structure of our Earth. Here you can see that we have named each of the layers of our Earth on this side and the boundaries on this side. We have also mentioned the distance and the thickness of each of these layers. So if you want, you can pause the video and note down all these points. Now let's see the structure of crust. Crust is the outermost layer of our Earth. This is the layer on which we live. This is the layer we see. The crust can be divided into two parts, oceanic crust as well as continental crust. Oceanic crust is made of SIMA, that is silicon and magnesium. The rocks are mainly of mafic type, that is rocks have mainly minerals made from magnesium and iron. Basalt is the most common type of rock in the oceanic crust. For the continental crust, we can see that we can divide it into two parts. The upper part is SIAL in nature, that is it has mainly silicon and aluminium, while the rocks have minerals formed of iron and silicon, that is why we call it felsic in nature. The lower part of the continental crust is again SIMA in nature, made of silicon and magnesium. The rocks are mafic type. Now the lower layer of continental crust, though made of SIMA, is different from the SIMA of oceanic crust. The reason is that the oceanic crust is formed at the mid-oceanic ridges, while the SIMA of the continental crust is formed by metamorphosis of the rocks lying above it. That is why both of them have different characteristics. Now let's see the continental crust in detail. The continental crust can have thickness of around 30 to 40 km, but under Himalayas it could go up to 70 kilometers. Now this value of 70 kilometer comes from a theory of isostasy, which says that every place the land masses exert a downward force. This downward force is due to the gravity. This downward force is balanced by an upward force, which is buoyancy applied by the asthenosphere. So everywhere these two forces are in balance. Now like an iceberg, for a small part of iceberg to be above the sea surface, a large part of the iceberg is beneath the sea surface. Similarly, isostasy said that for a land mass to be above the land surface, there must be a large amount of land mass below the earth surface, and this value comes around 8. So if we see, the height of Mount Everest is around 9 kilometers. So if you multiply 9 by 8, we get the value 72. So here it comes that the depth of our crust under Himalayas is 70 kilometers. The density of our continental crust is 2.7 gram per cubic centimeter, and this is the least dense layer in the earth. Now we have seen in planetary differentiation that the layers were differentiated based on their density. Since our continental crust is the least dense layer in whole of the earth, it was on the outermost side. Temperature of the continental crust could be around 200 to 400 kilometer at the Mohorovicic discontinuity. Now this is the boundary of our continental crust. This is the lower boundary of the continental crust. Now let's see the composition of continental crust. So we have seen that the continental crust can be divided into two parts, upper and lower. The upper part has SIAL in nature, while the lower part was SIMA in nature. Upper part had felsic rocks, the lower part has mafic rocks. Granite is the most common rock in the upper part of our continental crust, and feldspar is the most common mineral. In fact, feldspar is the most common mineral in whole of our Earth's crust. Sedimentary rocks are formed at the surface of our Earth. We will see this in great detail in another topic. But sedimentary rocks are the most common rocks on the surface of our Earth, while at the lower levels we see igneous and metamorphic rocks, which are in abundance. Now continental crust is formed at the subducting margins or at the convergent boundaries. Here two plates generally move towards each other and one of the plate moves under the other plate. Now when one of the plate is oceanic crust, what happens that the subducting plates will give rise to volcanic activities. These volcanic activities will add to the continental crust. Moreover, there are sediments lying over this oceanic flow. When it subducts, these sediments are also from the continental crust, therefore they wouldn't subduct because the sediments are also of less density, and that is why these sediments are added to the continental crust, and that is why we say that continental crust is formed at the converging boundaries. Now remember, continental crust never subduct. Even if two continental plates move towards each other, the mantle of one of the plates will move down in the asthenosphere and melt away, but the continental crust, as you can see, will never subduct. The continental crust of one plate will move under the continental crust of another plate, and therefore we see that there is a crustal thickening, but the continental crust will never subduct, and that is why continental crust can be of very high age. We can see that in Jack Hills of Western Australia, the rocks which were found were 4.4 billion years ago. Now these rocks, which are very old, which are like 3 to 4 billion years old, are called cratons, and they can be found in almost all continents. We have already seen that the continental crust can be divided into two parts, the upper lying SIAL type continental crust and the lower SIMA type continental crust. Now the boundary between both of these continental crust is called Conrod discontinuity. The reason why we call it discontinuity is if we send a seismic wave, its velocity will change at these margins. The velocity of the seismic wave changes at the margin of each layers. Therefore, these margins are called discontinuities. Here, the Conrod discontinuity is the margin between upper SIAL type continental crust and lower SIMA type continental crust. These Conrod discontinuities are not seen everywhere. There are certain regions where this SIAL continental crust will extend till the lower margin of continental crust. Moreover, the SIMA type layer of continental crust is different from the oceanic crust because the oceanic crust is derived at the mid-oceanic reaches. They are formed by the upwelling magma, while the SIMA of continental crust is derived by the metamorphosis of the overlying rocks. That is why they are different in characteristics. Now let's see the oceanic crust. The oceanic crust thickness is around 5 to 10 kilometers. So you can see that it is thinner than the continental crust. The density is 3 gram per cubic centimeter. So it is slightly denser than the continental crust, whose density was 2.7 gram per cubic centimeter. Temperature at the Moho would be same as our continental crust. The chemical compositions, we have already seen that it is mafic in nature, that the rocks are mainly made of minerals from magnesium and iron. Silicon and magnesium are the most common elements, and basalt is the most common rock. We have already seen these points. Oceanic crust is formed at the diverging boundaries. So we have seen that this is a diverging boundary and there is an upwelling magma. This magma, when comes to the surface, it cools down to form the oceanic crust. Therefore, oceanic crust is formed at the diverging boundaries. Here both of these plates are moving away from each other. While the oceanic crust is destroyed at the converging boundary. Here we can see that at a converging boundary, oceanic plate is subducting and it will be melted in the asthenosphere, and that is why it will be destroyed. So we see that the oceanic crust is continuously formed and destroyed. There is a continuous cycle. While compared to this, continental crust does not subduct, but it is formed little by little at the converging boundaries. Now, because of continuous recycle of our oceanic crust, what happens that they are of very young age. The oldest oceanic crust was of Ionian Sea, that was 270 million years old. So you can see where the continental crust is billions of years old, the oceanic crust is only 270 million years old. So this is very young. Now let's see the difference between oceanic and continental crust. This could be a very good question for your exam, to write the difference between the oceanic and the continental crust. So the continental crust is formed at the converging plates. We see that at the converging plates, the oceanic crust will go below the other plate and there will be volcanic activities which forms the continental crust. Moreover, there are sediments on the oceanic floor which will be added to the continental crust. So we see that the continental crust is formed at the converging plate boundaries, while the oceanic crust is formed at the diverging plate boundaries. Why? Because the plates are diverging, the magma will come up and it will solidify and forms the oceanic crust. This happens at mid-oceanic ridges in the seafloor generally. Now, we have seen that the continental crust never subducts because it has low density. As it has low density compared to the mantle or asthenosphere, it will never subduct because the buoyancy force on these rocks will be very high and so it will be pushed away. While the oceanic crust does subduct at the converging plates, we have seen when there are two plates and one of them plate is oceanic plate, so it will subduct because it is more dense. Now we have seen that continental crust do not subduct. Therefore, the rocks are very old in the continental crust. They could be as much as 4.4 billion years old. However, because the oceanic crust is continuously recycled, it is continuously formed, it is continuously destroyed. And that is why the rocks are not much old, but they are as old as 270 million years. This is the oldest rock that we could find. We have already seen that the continental crust is SIAL in nature, while the oceanic crust is SIMA in nature. The thickness of continental crust is more, that is around 30 to 40 km, while the thickness of oceanic crust is only 5 to 10 km deep. They have felsic rocks where granite is the most common rock, while these are basaltic rocks which are mafic in nature. So oceanic crust is mafic in nature. Mohorovicic discontinuity is the discontinuity between the continental crust and the upper mantle. The depth of this Moho discontinuity could be 32 kilometers under continents and 8 kilometers under seas. However, the depth of this discontinuity is not constant because of the principle of isostasy, which says that the downward pressure applied by the gravity on a landmass should be balanced by an upward force in the form of buoyancy from the asthenosphere. So these two forces must be in balance. Now for that to happen, the region of land area where there are large land masses above the surface, there should be large amount of land masses below the surface. So here you can see that there is large land mass above the surface, so there is large land mass below the surface. While here there is small amount of land mass above the surface of Earth, so there is small amount of land mass below the surface of Earth. So because of this principle of isostasy, we see that the Mohorovicic discontinuity is not of uniform depth. The depth will vary depending on the amount of land mass above the Earth's surface. Let's see the structure of upper mantle. We have already seen the oceanic crust and the continental crust. The layer below the crust is upper mantle. It is separated by the crust through the Mohorovicic discontinuity. Now, the upper mantle is further divided into two parts. The first is the brittle upper mantle. These are hard in nature, and if you break, they will break. Well, this is asthenosphere. This is plastic in state. It is very ductile in nature, so it can be formed into any shape. This is in semi-solid kind of state. Everything above asthenosphere is called lithosphere. So you can see that lithosphere includes the continental crust as well as the brittle part of upper mantle. Now remember, the chemical constituents of both of these layers are similar. It is the mechanical properties of both of these layers are different, and that is why they are classified into single upper mantle. Upper mantle extends till the depth of 670 kilometers from the surface of our Earth. The thickness of upper mantle is around 640 kilometers, but you can see that it is only 20% of the total mantle, that is the upper and inner mantle combined. So compared to the inner mantle, upper mantle is very small. Temperature can range from 1000 to 1800 degrees Celsius. Density, as we see, is increased. The oceanic crust was 3 gram per centimeter, and this is 3.4 gram per cubic centimeter. This is divided into two parts, which we have seen. The lower part is asthenosphere, the upper part is lithosphere. Both have similar composition but different mechanical properties, which we have already seen that the asthenosphere is ductile. That is, it can be formed into any shape. It is in plastic state or it is in semi-solid shape, while the lithosphere is brittle, it is hard. Lithosphere includes crust as well as upper brittle mantle. Lithosphere is the plates, which we call in plate tectonic theory. So it is the lithosphere which gives rise to plate tectonics theory. Lithospheric plates float on the asthenosphere, and which causes the plate movement. So our lithospheric plates move on the asthenosphere because asthenosphere is in semi-solid state. It provides very low friction to the moving plates. Let's see lithosphere in detail. The lithosphere could extend till 200 kilometers. The thickness of the lithosphere is around 100 to 200 kilometers. Now remember, this is max and min region. The average thickness of lithosphere would be around 100 kilometers. The value in different books would vary slightly because these values change over time due to different models used for measuring them, and different organizations provide different values used based on their own findings. That is why if you see another readings in your books, then please use them. Now the thickness is less at mid-oceanic ridges because at the mid-oceanic ridges the upwelling magma will thin the overlying plates, and that is why the thickness of the plate is very low in the mid-oceanic ridges. While in the subduction areas where the plates are sinking, the overall thickness of the lithosphere increases. The density is 2.7 to 3.3 gram per cubic centimeter. We have already seen that the lithosphere is crust plus upper brittle mantle, and it is divided into several parts. Each of these parts is called a tectonic plate, and these tectonic plates float on the asthenosphere, and it is movement of these plates that give rise to seismic activities like earthquakes, volcanoes, formation of trenches, formation of fold mountains. So all of this is because of lithosphere moving on asthenosphere. Now let's see structure of asthenosphere. Asthenosphere is part of upper mantle. We can see here that asthenosphere is part of upper mantle. Its density is around 3.5 to 4 gram per cubic centimeter. The temperature could be from 1400 to 1600 degrees Celsius. The thickness can be from 100 kilometer an average value to 410 kilometer an average value. So this is the thickness of our asthenosphere, around 300 kilometers. The asthenosphere is mainly in plastic state, and the reason can be derived from this graph. Here we see a melting curve for rocks. If the rocks are on this side of this curve, they will be in molten state. This is the temperature axis, this is the pressure axis. The pressure axis is analogous to the depth of our Earth. So what we see in the asthenosphere, the rocks, their temperature and pressure profile is very close to this curve, and that is why they are in semi-solid state. The asthenosphere, because of being very close to this melting curve, are in ductile state. That is, we can very easily change their shapes. They are in some kind of jelly kind of state. When seismic waves pass through them, their velocity suddenly changes. You can see here for both S waves and P waves, there is a slight change in their velocity. And this is how the asthenosphere was discovered. Let's see the importance of asthenosphere. We have already seen that the lithosphere is divided into different parts, and each of these parts is called a tectonic plate. And the tectonic plates move on the asthenosphere. And because of the movement of plates, we see all the seismic activities like the volcanoes or the earthquakes. Asthenosphere is also a source of isostasy, where we have seen that a buoyancy force is applied by the asthenosphere in the upward direction against the gravity of the land masses. The continental drift and the volcanoes are caused because of the asthenosphere. Most of the magma in the volcanoes on the surface of Earth comes from the asthenosphere. Here you can see that this is a diverging boundary where the magma is coming to the surface and forming oceanic crust. While here we see a volcano. In this volcano, the volcano rises up from the asthenosphere. Moreover, the convection cell of magma that continues in the asthenosphere is also the source of the force which causes the plates to move. That is why we can see that asthenosphere is a very important layer. Now at the trenches, what happens that the oceanic crust will subduct, and in the asthenosphere they will melt. While at the mid-oceanic ridges here, the lava from the asthenosphere comes up, solidifies and forms new oceanic crust. So we can see that the asthenosphere recycles the lithosphere. It destroys it at the converging boundaries and forms new lithosphere at the diverging boundary. Between the outer mantle and the inner mantle, there lies a zone which is called a transition zone. Here the rocks change their characteristics from semi-solid nature of asthenosphere to solid. This boundary is also called as Repetti Discontinuity. Now this is not a thin boundary but a very thick layer where the characteristics change slowly. As we go deeper and deeper, the rocks will become more and more dense across this discontinuity. Moreover, because of the thickness of this transition zone, it prevents the rocks which are subducting from the lithosphere to mix with the inner mantle, and that is why the mixing is very less. Now let's see the structure of inner mantle. Inner mantle is the layer which lies below the upper mantle and above the outer core. This is solid in state. Its depth starts from 660 km to 2900 km, and the temperature can be from 1700 to 2800 degrees Celsius. The density could be from 4.4 to 5.7 gram per cubic centimeter. So you can see that the density of the rock layers increases as we are going deeper and deeper. The inner mantle is hotter and denser, but even though being so much hot, it is not in a molten state or semi-solid state like asthenosphere, mainly because of the overlying pressure of the rocks. There is so much pressure that it prevents the rocks from softening or melting. That is why the inner mantle is in solid state. Now the inner mantle contains approximately 56% of the total Earth's volume. So you can see that this is the single biggest layer of our Earth. If we combine it with the outer mantle, we can see that it is 83% of the total Earth volume and 46% of Earth's radius. So you can see that this is how big the mantle is. And its main constituents are magnesium and silicon. That is, it is SIMA in nature. So that is why all the magma that comes from inner mantle are SIMA in nature, and when they form the oceanic crust, it is SIMA in their characteristics. Gutenberg discontinuity. It is a discontinuity between the outer core and the inner mantle. You can see here it is around 2900 km deep. Now the S waves cannot pass through this discontinuity. You can see here this is Gutenberg discontinuity, and our S waves cannot pass through them. The P waves which do pass through them, their velocity is very highly reduced. You can see here this was the velocity just above the Gutenberg discontinuity, and this is how it is reduced. Moreover, the P waves undergo a large amount of reflection as well as refraction. So you can see here how much they are bent. This is showing refraction only, but they also go reflection. Now let's see the structure of outer and inner core. The outer core starts from 2900 km and it extends till 5100 km. The density can be from 9.9 to 12.2 gram per cubic centimeter. The temperatures can vary from 3000 to 5000 degrees Celsius. Now this is the only layer in whole of our Earth that is in liquid state. We have seen that there is only one layer, that is the outer layer, which is in liquid state, while there is only one layer which is in semi-solid state, that is our asthenosphere. S waves do not pass through this layer. We have already seen that the Gutenberg discontinuity does not allow the S waves to pass through them. The P waves, they pass through the Gutenberg discontinuity, but their speed decreases because outer core is liquid in nature. It is mainly formed of nickel and iron. Now one interesting thing about the outer core is that the outer core rotates opposite to the direction of rotation of our Earth. So we see that the Earth rotates from west to east while the outer core rotates from east to west. Moreover, our outer core is mainly made of nickel and iron, both of which are magnetic elements. Moreover, it is in liquid state and it rotates. That is why the iron is in continuous motion. And because of this continuous motion, there are large discharged currents produced within the outer core. And it is because of those we see magnetic field lines produced across our Earth. So the source of our magnetic field is our outer core. Inner core is the innermost layer of our Earth. It lies at the center of our Earth. The speed of the P waves increases as they come from the outer core to inner core, mainly because this inner core is in solid state. It is in solid state because of the pressure of the overlying rocks. The depth is from 5100 km till 6371 km, which is the center of our Earth. Its radius is around 1200 kilometers. The density varies from 12.8 to 13.1 gram per cubic centimeter. So this is the most dense layer in whole of our Earth. So remember, right from the top till the bottom, the density continuously increases. The temperature is about 5200 degrees Celsius. This is greater than the melting temperature of our iron. But iron is in solid state here because of the overlying pressure. Again, our inner core is made of iron and nickel, so we call it as a Nife. The inner core rotates in the normal direction of our Earth, so even it rotates west to east, like our Earth rotates from west to east. Lyman discontinuity separates outer and inner core. So here we see that this is a Lyman discontinuity which separates the outer core and the inner core. Now let's see the concept of convection cells. In 1929, Arthur Holmes said that within the mantle there lies a lot of radioactive elements. And these radioactive elements, when decay, they generate a large amount of heat. But these radioactive elements are unevenly distributed, as you can see. So the places where they are concentrated, they will generate more amount of heat. And because they generate more amount of heat, they will melt the mantle here. You can see here, this molten mantle is of less density and is hot. So it starts to rise up. It rises up, reaches the asthenosphere, moves horizontally, cools down and comes back. So this is how he proposed that there lies a convection cell within our Earth, and this convection cell is the cause of most of the movement of plates on the surface of Earth. Now there are two variations of this concept. There are few scientists who believe that there is a single convection cell, that is, the magma starts from somewhere lower portion of the inner mantle, comes to the asthenosphere, moves horizontally, cools down and goes back. So this is the whole cycle. Now there is another school of thought which believes that there are two convection cells. In the first convection cell, the magma rises from the lower part of inner mantle, rises up to the upper part of inner mantle, and then it moves horizontally, cools down, comes back. Because of this hot magma here, it heats the magma in the asthenosphere, and this magma then rises up, moves horizontally, comes back, moves horizontally, and the cycle continues. So this is a dual convection cell model. Now we will see the distribution of different minerals and elements in our Earth. We will first begin with the most abundant element in Earth crust. Now remember, we are talking about elements in Earth crust and not our whole of Earth. Earth crust is the outermost layer. Oxygen forms almost 46% of the whole earth crust. So it is approximately 50% of our whole of our earth crust is made of oxygen alone. Then silicon is also approximately half of oxygen. It is 28%, followed by aluminium, iron and calcium. If you want to remember the order of these elements, you can use the mnemonic OSI. O stands for oxygen, S for silicon, A for aluminium and I for iron. Now let's see the most abundant element in whole earth. Earlier it was only earth crust, now we are talking about whole earth. Iron is most abundant element in whole earth. It forms 32% of the earth. That is, almost 1/3 of our earth is made of iron. Similarly, approximately 1/3 of our earth is made of oxygen. So we can see that iron and oxygen, they form more than 60% of our whole earth. Silicon, magnesium and sulfur follow these elements. The mnemonic for remembering the top 3 elements is IOS. Next, the most abundant mineral in earth crust. Minerals contain of different types of elements, whereas an element is a single type of atom or molecule. So you can see here that now we are discussing minerals. Most abundant mineral in earth crust, this is our continental as well as oceanic crust, it is feldspar. It forms almost 52% of our whole earth crust. So more than 50% of our earth crust is formed of feldspar alone, followed by quartz, pyroxene, amphibole and mica. If you want to remember the first 2 minerals, you can use the mnemonic Feku. If you want to remember all of these elements, then you can use the mnemonic Feku Pam, Pam, P-A-M. Now let's see the most abundant minerals in different parts of our earth. The whole earth, the most abundant mineral is brigmanite, because it is the most abundant mineral in mantle, and we know mantle is the biggest layer in our earth. The most abundant mineral in crust is feldspar, while the most abundant mineral in core is taenite. If you want to remember these 2 minerals, you can use the mnemonic FB, Facebook, or you can use it FBT. In this table, we have summarized everything that we have discussed: their depth, their thickness, density, temperature and types of rocks found. So I hope this table will help you revise the whole topic in a very short time. Now here we can see the discontinuities. The Conrod discontinuity, their depth, the layers between which they are found. We have noted down all this for you, so you can note it down and use this for your exams. Now, to remember the order of the discontinuities, you can use this mnemonic common rasgulle. So here it is like you are saying your friend, come on rasgulle, where CO stands for Conrod, MON stands for Mohorovicic, R is for Repetti, and GU is for Gutenberg, and last is for Lehman. So this will help you remember the order of the discontinuities. Come on rasgulle. If you like the video, then please like, subscribe and share. If you like what we are doing and if you want to support us, then you can use our UPI ID as well as Patreon ID. All the things we have discussed here is available on our website zeta-access.com, so do visit it. Please follow us on our social media links provided here. And till the time we meet again, Jai Bharat, Jai Gyan. Thank you.